Okay, so today's presentation is an attempt to explain how we as geographers produce maps through map projection and important aspects of those maps once they're completed. So the first question here is, what is a map projection? So we imagine a map projection in the same way that we imagine what happens when we are watching a movie or watching a presentation on screen. A projector in a movie theater or in a classroom takes a three-dimensional object and turns it onto a flat surface. Well, the same thing is being done when we look at how we take a globular object such as the Earth or an oblate spheroid and turn it into a flat surface on a map so that we can better evaluate phenomena that occur on the globe. So essentially what we're taking is this three-dimensional object and we are stretching it out so that it can be used on a flat surface. So the formal definition is that projection is the scientific method of transferring the location on Earth's surface to a flat map. And all map projections distort some portion of the map based on either distance, direction, shape, or relative size. And we'll go through some examples of how that's done and the impact it has on what a map looks like and why that sort of distorts the shape of the Earth, but it also distorts our understanding of what we're looking at. And in many ways, it can be used as a tool for propaganda, and we'll talk about examples of that here in just a minute. So there are three main methods: cylindrical, conical, and planar. Cylindrical, essentially imagine putting a cylinder around this globe here on the right side of the screen, and then taking everything that is on that globe, stretching it out to fit on a flat surface, cutting that flat surface down on one side, and then stretching it out on a table. And so you see here where there's equal distances between the lines of latitude on the globe. Once it is stretched out, those equal distances are no longer equal. They are stretched out. And so it has an impact on the shape of the continents that appear on this particular method, cylindrical method of projection. Next we have conical. And a conical is often used to map mid-latitude areas, so it's accurate if we're attempting to show the United States without consideration of Alaska. So if we want to accurately represent the United States, then we might use a conical projection as opposed to a cylindrical projection. Same thing can be said if we want to accurately represent Europe. We would use a conical projection. As you get further from the mid-latitude or the center latitude of the map, it then becomes more and more distorted. And you can see that here becomes more and more distorted as you get further south. And the same can be said for the cylindrical. As you get further from the equator, it becomes more and more distorted. And then finally, there's planar. Planar is often used to project, that method is often used to project the poles, so either the North Pole or the South Pole, because the most accurate portion of a planar projection is the very center point. As you get further from the center, everything, all shapes, sizes, distances, everything becomes massively distorted and it would be unrecognizable. So essentially the same idea, we're taking as if we're taking the skin off of a peach, or excuse me, yeah, I guess we could say peach, or an apple skin, and we cut it, slice it, and attempt to stretch it out to be a perfect circle. This is an example of planar. All right, so Mercator projection is an example of this sort of cylindrical method. And as you can see by Mercator, which is the common method that Google Maps uses, everything is highly distorted as you get further and further away from the equator. So the most accurate portion of this map is along this equatorial line. But as we get closer and closer to the poles, everything becomes more highly distorted. And you can get a better view of that here. Antarctica is not that big, and neither is Greenland. So if you look here, there's a link. What's up with this? You can get a better view of this at the true size of And so let's see what Greenland really looks like compared to the rest of the world. So I type in Greenland. So here's Greenland on the Mercator projection. Because it is close to the pole, it's highly distorted. But if we're to remove it from the pole and move it to the most accurate portion of the map, which is at the equator, notice how much smaller it is in reality. So this particular map distorts our view of what the world really looks like. And for years, it was used as a propaganda tool to make Europe appear larger compared to Africa and South America. But it is the standard projection for nautical purposes, and that's because Gerardus Mercator, the creator of this map, made it specifically designed so that it could be used by sailors and traders from Northern Europe, so that they could use it more easily to determine direction. Since all the lines are parallel, it makes it easier to map shipping routes. Now on the opposite end, we see the Mollweide projection, which attempts to take the entire globe and be as accurate of size towards the poles as possible. But the problem is when you try to keep the poles accurate in size, what does it do? It then distorts the shape and angle. Primarily used where accurate representations of area takes precedent over shape. And then on the opposite end, Robinson attempts to take the Mercator projection and then combine it with the Mollweide and produce a composite projection, or a compromise projection, as it's been called. Now, the problem here is that it distorts everything just a little bit, but it makes a handsome view of the Earth. So it looks nice. This particular map, because it distorts everything just a little bit, has no use when it comes to statistical evaluation or even geographical evaluations of phenomena across space, but it is good if you want to just show a phenomenon to a group of people, because it's nice to look at. Often used in textbooks. And then here's the Azimuthal equidistance projection, and we can see here what it does to the shapes. As you get further and further from the center, the shapes are represented by these circles, the accuracy of the shape. As you get further and further from the center, you see that the heavy distortion of these circles until you get to the outer edge, and it makes Antarctica appear like a giant wall surrounding the Earth. And then here's the actual map of the azimuthal equidistance projection. And then we have Goode's Homolosine projection, which is the most accurate map as far as size shape is concerned. But the problem is it's not very accurate for distances because it does cut the oceans in half. So you can imagine the process of doing this is like peeling a peach skin and stretching it out to fit on a table. A similar method used in the Fuller projection. So Fuller projection, highly accurate when it comes to land masses, but the directions are unusable. So if you want to represent shapes and sizes of land masses accurately, this is a great map to use, but it wouldn't be very usable if we're trying to represent migration patterns of a particular bird, etc. And then finally we have Peters projection. Now there are hundreds of projection styles. I won't be able to go through all those, but this will be the last one that we discuss in any great detail. The Gall-Peters or Peters projection is politically driven and politically motivated, and there's a reason why. Up until its creation, the common map projection was used by most textbooks, etc., was the Mercator projection. And as you can see, Mercator projection makes the northern hemisphere look much larger than the equatorial region, and so it was used as a propaganda tool to show supremacy of European imperialism over the equatorial region. And so as a countermeasure, Gall-Peter projection attempts to do the opposite. Rather than distorting Rather than making the poles look larger than the equatorial region, what they did is instead made the poles look smaller than the equatorial region. And you can see that here. Rather than making these parallel boxes equal size, they clearly distorted the equator to make it look bigger, and then distorted the polar region to make it look smaller. So this is also highly inaccurate when it comes to shapes and distances as well. If you want to take a minute, you can look at some of these websites. I won't go through these, but you have access to this online. You can take a look at the, let's see, that's not right. You can take a look at the Jason Davies map projection website, and this goes through the transitions. Some of this stuff's pretty interesting. We can look at, let's go to the Mercator projection. So this is the Mercator projection. This is the way that that it's mostly represented in on maps. But we can see what it does to the shapes and sizes of objects if we just move it a little bit. So what if we wanted to center the map on Greenland, which is highly inaccurate if we show it like it normally is shown. And you can see how it distorts everything else. It really changes your perspective on the shape and sizes of land masses across the Earth. So take a minute, look at and play with these. It's quite interesting. I'm not going to go through these. Take a minute and look at these if you want to. This will help test your understanding of projections. When might you use one of these? I've already kind of given one away. Mercator is best used if you're a boat captain. So take a look at these and try to test your knowledge of map projections. All right, so last thing that we'll talk about is map projections, or excuse me, map properties. So what are 4 things that are required on all good maps? First, all good maps need to have a map title. Second, a legend or a key. Third, a scale. And fourth, a compass rose. We need to know directions, we need to know sizes, and we need to know what the things on the maps mean. And we also need to know what is the purpose of the map. And so that's what all these things will tell us. So if you go to this link right here, as you can see, I've already gone to it, Katrina Alago Blogspot. So I'll go to that here. Read through this, but she gives some examples of good and bad maps. So this is a great example of a terrible map. So if we expand this map and get a better view of it, what is this map showing? There's no title, there's no legend, there's no scale, and there's no compass rose. So we don't know what direction is north. We don't know what any of these symbols mean, and we don't really know the purpose of this map. So this is an example of a good map. Now, it may not be your favorite looking map, but it does accurately represent what it is attempting to show. Local services in East Los Angeles, there's a title. We have a legend. We have a compass. We have a source for the map, the Urban Institute Justice Policy Center. And we also have a scale. So this map has all the 4 important parts of a good map. So what exactly is a scale? Now a scale attempts to tell us the actual distance on Earth that is being represented by the map itself. So in other words, if we see on a scale like here, 0 to 1, so this distance equals 1 mile in real life. So it's easy for us to take a ruler and then measure the distance here and do it on a map, and then we can say, oh, well, from here to here is roughly a mile. But there are 3 main types of scales. One is a verbal scale. Another is a fractional scale. And another is a graphical scale. So the verbal scale is just a definition. It's just an explanation of the size as it is represented on the map compared to real life. A graphic map scale attempts to give us and this is usually what we're mostly used to on maps, it gives us distances at the bottom represented by a line that tells us, from this particular place to this particular place equals roughly 50 miles in real life. And this is the most common method. Most people use this, and this method is most people's favorite method for attempting to understand true distances on Earth. However, my favorite is the fractional scale, and there's a reason why. If you use this particular scale, it means that you're limited to only kilometers and only miles, or in this case, only miles. Well, what if I wanted to know centimeters or inches? Well, then I'm going to have to translate kilometers or miles into centimeters or inches. However, if I have a fractional scale, I don't need to do that. A fractional scale shows it as thus: 1 to 50,000. 50,000. So in other words, whatever 1 on the map is, equals 50,000 of that in real life. So I can use centimeters, inches, miles, whatever I want to use. So if I want to use centimeters as my form of measurement or method of measurement, then on this particular scale, 1 centimeter on this map equals 50,000 centimeters in real life. Fairly simple to use. I'll go into more detail of large scale versus small scale here in just a little bit. And then also the last thing on this slide, aerial differentiation versus aerial integration. So as cartographers and map makers, we try to use those maps to measure differences and similarities across space. So these are antonyms from one another. Aerial differentiation just means the spatial distribution of physical and human phenomenon as they relate to other spatially proximate and causally linked phenomena, blah, 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 blah. So we would use aerial differentiation to see how things are different across space. And then we would use aerial integration to ask how people and things work together across space. So how are they integrated? How are they linked to one another? All right, so here is a map that I made that has the 4 basic principles. So this is Greensboro, North Carolina. Here is a legend. And here is all different types of scales. We've got the fractional graphical scale. I do not have the verbal scale on here. But we also have the compass rose. So this is an example of a good map. All right, here are some examples of different scales. So we have different types of scale. Scale, the level at which an area is viewed geographically on Earth. So we have local scale, regional scales, and then we have international or global scale. So this is UNCG within Greensboro, North Carolina. Greensboro, North Carolina within Guilford County, Guilford County within North Carolina within the southeast, U.S. within North America, and then North America on Earth. So when we want to describe these maps as either large or small or middle scale maps, it becomes a little confusing, but keep this in mind. When we refer to something as large scale, it doesn't refer to the map itself, it refers to the items being represented on the map. So if the items on the map are larger in appearance, then that is a large scale map. So this right here is a large scale map. Although it is zoomed in closer, and cognitively we want to say, oh, that's a small scale map because it's a smaller area. But it is a large scale map because it shows objects larger than they would appear in a map like this, which is the smallest scale map that you can get. So just keep that in mind. This is a large scale because objects are large and it's zoomed in. This is a small scale map. And this gives you a better idea. If you want to look at this at home, I'm not going to go into any detail, but we see large scale here, small scale here. So the closer you zoom in, the larger the scale. Large scale represents fractional, large representative fraction, small denominator, shows a smaller area but with more detail. So your fractional scale here, 1 to 1,300,000. and then in this one, which is a small scale, 1 to 95 million. Small scale, small representative fraction, large denominator. It shows a larger area but with less detail. Okay, so the last thing that we'll talk about today is our latitude and longitude. So the common misconception is that they're simply just lines on a map, and while that's somewhat true, it's not completely true of sort of the basis of what these particular measurements are attempting to show. So the maps on a piece of paper or on a map. Okay, so the last thing that we'll discuss today are latitudes and longitudes. So the common misconception is that latitude and longitude are just lines on a map. And while they are represented by lines, they are something much more than that. They are measurements of angles. The lines on the map are also known as meridians and parallels. And hence, when you look at the lines on a map, you'll say line of latitude or line of longitude, or you might call them parallels and meridians. But latitude and longitude themselves aren't lines. In fact, they are angles as measured from the center of the Earth. And so when we look at something like 30 degrees north latitude, it's actually 30 degrees angle from the center of the Earth as compared to the equator. So the equator is 0, and that's hence because it's measuring the angle to itself. So if we're looking at the parallel line, or the line of latitude of 30 degrees north, it gets the term degree based on its angle from the center of the Earth as it is compared to the equator. And the same thing can be said for 0 degrees longitude, angles as it compares to the east and west as it compares to this prime meridian out of Greenwich, England, or the greater London area. And so because of the importance of GPS location and coordinates and distances based on the angles from the center of the Earth, we have some major lines of longitude and latitude. Now, the two major types of longitudinal lines, or meridians, are the prime meridian and the international date line. Technically, the international date line is not a line of longitude or a meridian, but it's a measure of time. Well, I won't go into any detail on that. The reason why it's not considered a line of longitude or a meridian per se is because it's not a straight line. It bounces back and forth as to avoid islands, because they don't want to cut islands in half, because when you cross over the date line, you're literally moving either back a day or forward a day, depending on the direction that you're moving. And then the prime meridian is based around London. Some consider it a tool of imperialism, because essentially they're stating that we are the center of time in London. So it is interesting how that just happened to work out that way. And then the major lines of latitude, or the major parallel lines, the Arctic Circle, Antarctic Circle, Equator, Tropic of Cancer, and Capricorn, and then of course the North and South Pole. These major lines of latitude are based around the angle of the sun. So I've got this sort of diagram here with the watermarks on it, titled Earth's Vital Areas. And as you can see, the sun's rays and what's represented here is the summer solstice in the northern hemisphere. The Arctic Circle is at 66.5 degrees north, and it is an important line because during the summer solstice in the northern hemisphere, everything from this line, everything from 66.5 degrees north to 90 degrees north, or the North Pole, will have 24 hours, at least on that day, 24 hours of sunlight. And the same can be said, or the opposite can be said when it is the winter solstice in the northern hemisphere. You'll have everything above that line for at least one day will have 24 hours of darkness. And then the other major lines, Tropic of Cancer, 23.5 degrees north, Tropic of Capricorn, 23.5 degrees south, again, based on the angle of the sun. So during the summer solstices in either the northern hemisphere or the southern hemisphere, the sun's rays are directly overhead these tropical lines. And it's called tropical lines because it's often seen as the barrier between tropical climates as well. And then, of course, the equator, 0, it is important for two reasons. It's the center of the parallel lines, but it's also it also receives direct sunlight twice a year, and it's because it does that on both equinoxes rather than solstices, then it is important for that very reason. So just keep that in mind when it comes to lines of latitude and longitude. All right, that's it for us today. So if you have any further questions on anything that we've discussed, feel free to send me an email, or you can ask me in our next class. Have a good weekend.